So we now move on to triangulations of point sets. And as you'll see, these triangulations can be a bit different from the triangulations of polygons proper. But actually, the first thing we're going to look at, which is the triangle splitting algorithm, actually triangulates a polygon as part of the process. So in a formal sense, you can actually define a triangulation without actually mentioning the word triangle. So it's effectively the maximal set of non-crossing edges between the points in the input data set. So just to start off with this sort of fairly straightforward algorithm, we basically have 4 steps. The first is to find the convex hull of the point set, which we've just learned how to do. The next step is to triangulate the hull as a polygon. So the first step we can do in Python, and the second step we can do in Python using the triangle library, which again is an API to the low-level triangle library. And then step 3 is sort of, and step 4 together are sort of these iterative steps where you pick an interior point within the initial triangles from triangulating the convex hull, and you draw edges from that interior point to the 3 vertices of the polygon that contains it. And so then each time you do that, you form 3 new triangles within the original triangle. And you continue this iterative process of taking the internal points of the new triangles and drawing edges from that point to the edges, or to the vertices of the triangle that contains it. So we'll go through this in a sort of step-by-step fashion, but just to show you the visual result first, so you can have a sort of a better idea of what we're trying to do, we basically take this data set, which is a random set of points, and I've here initially set it to, let's see, how many points do we have here? Here it is. So we have 10 points in our data set. It's a 2-dimensional planar data set. We run our code with these random points. You can see that the convex hull is plotted right here through these outer data points. And then we've done the triangulation on the polygon, which corresponds to the convex hull. And then we've produced a number of triangles as a result of that. So there's 4 triangles here. And then what we do is we take each of those triangles and we look for points that are inside of them. So this point here, and this point here, and this point here. So if you start with this point here, for example, there's a really skinny triangle that goes from this vertex here, to this vertex here, to this vertex here, and from this vertex here, to this vertex here, to this vertex here is another triangle. And so you draw a line from here to here, a line from here up to here, a line from here up to here. And you split this large initial triangle into 3 other triangles, and then you either take this point or this point, which is inside the new triangle. You do the same thing, and you can actually see that happening iteratively here. So that initial skinny triangle is visible here, between this point and this point, and this point up here. It's very, very skinny in that particular region. You can see the point from here, the edge from this point to this point here, and then we have another triangle forming with, sort of taking this point over here and triangulating with that one. So we draw a line from the original to this one to this edge, and this one to this edge, and then we do the iterative process one more round with this point here, so taking this one here inside the new triangle that was formed in the last round, and basically producing 3 new triangles once again. And because none of these 3 new triangles contain any additional points, we finish the process of triangulating the point set. So you can see we're actually using what we learned before. We're calculating the convex hull, and then we're using the constrained triangulation from the triangle library, and then after that we're using this new approach where we actually triangulate the point set from that starting position by drawing edges from interior points to the edges of newly formed triangles in the process. So just looking at the code a little bit more closely now, you can again see we're using the scipy.spatial.convex hull on the point set. So that's our starting point, first step in the process. And then we're basically pulling out the segment indices because that's used as input to the triangle library. So this is the constrained triangulation, not the Delaunay triangulation, which we'll talk about in a little bit. And then we basically take the simplex coordinates from so this is the coordinates of the triangles, and we plot the triangles, which is just for the visualization purposes. And now we basically want to identify the interior points, as it says here, and draw the edges again to the vertices of the triangles that contain them until we run out of points to deal with. And the way the interior points are identified is basically by taking all the indices, so basically from 0 up to the number of points in the initial data set, and indexing that with basically the vertices that don't match between the full set of indices and the indices for the vertices of the convex hull. So anything that's not, so inversion is set to true, anything that's not on the convex hull is an interior point, because those are all contained within the convex polygon that surrounds the internal data points. Now the next part is a little bit trickier, and actually took me a little bit to get going properly. And this is this iterative process where you go through and draw those edges from the interior point to the vertices of the triangle that contains the interior point. You can see that here I'm actually using the matplotlib.path to define a path, and then the current path.contains points. So this is the method I was talking about much earlier in the presentation. We're checking to see if a point's inside a polygon, because that's important. We want to know if a point's in a polygon, because then we'll use that as the point that's the center point for drawing the three new triangles. So I effectively just draw. This is just plotting those points, and then also taking the three possible permutations of. So, for example, this point to this point, this point to this point, and this point to this point. The three possible permutations of edges from the center point to the vertices of the triangle, and combining those into the array of total simplices, of total triangles in the system, and then we plot all of those triangles in our final triangulation. So that, there's a bit of code there, but we're effectively using Python tools the whole way, and that's just on a very, very simple system. So you can imagine that for a much larger number of generators, for 100 points or for 1,000 points, that we'd want a sort of very well-refined algorithm with a practical time complexity to do these triangles. Otherwise, it would sort of take quite a long time to do it. And you can also imagine that there are actually quite a few different possible triangulations, because we could choose. This code here doesn't. It just basically goes through the points in input order, but you could easily choose this point first, and then this point, and then this point when you're doing the iterative triangulations, and that would actually produce unique triangulation structures. And it actually turns out that the number of possible triangulations for a point set is huge, and this is actually, within the last 10 years that mathematicians have been able to put an upper cap, an upper limit to the number of possible triangulations for a point set. So it's 30 to the power of n, which is absolutely enormous. In many cases, I suspect it's less than that, but this is the only thing that we can confidently say for sure, is it's 30 to the power of the n. The number of vertices or the number of points in the input data set is the upper boundary. But what we can do is say that with absolute certainty that the number of triangles in any point set is always fixed. So there's different permutations of the edges to produce different triangulations, but all of those triangulations will always produce the same number of triangles. So we have, and that number is from Euler's work a really long time ago, where we basically have this equation 2 times the number of interior points, which are k, plus the number of points that fall in the hull, minus 2 is equal to the number of triangles. So it turns out that this enormous number of possible triangulations, even for a relatively small input data set, can be fully explored in planar cases by something called a flip graph. And a flip graph is basically a set of nodes where each node is one of the possible triangulations for your input data set. And you know, the name basically comes from the fact that if you flip one of the edges, so if we look at this node here and compare it to the one just below it to the right here, the only thing that has changed is that this edge here has been flipped from horizontal, from this vertex to this vertex, to vertical. So it's from this vertex to this vertex. And it turns out that we know for sure that for all two-dimensional planar point sets, it's possible to go from one triangulation to another by traveling through the flip graph using edge flips. And in fact, there are many algorithms in computational geometry that exploit this fact to achieve a triangulation with a specific set of properties by progressively flipping edges to achieve certain property transitions. So this is effectively the space of triangulations of S. And the idea that all of these triangulations are connected, that you can interconvert them using edge flipping, was proven by Charles Lawson about 40 years ago. So flip graphs have many interesting properties, and you know, I'm not aware of any Python tool that would produce the entire flip graph for input data sets. So that might be an interesting exercise. I'm not sure if it would be super difficult, but it certainly strikes me as a non-trivial to get it working reasonably well. Certainly, I think it would be maybe fairly straightforward to do it in a way that's fairly slow, but getting it to work really quickly might take a fair bit of thought. You know, it's also known that well, we're not actually sure if the flip graph for three-dimensional space, so between edge visualizations, which presumably means flipping a face as opposed to just an edge, is fully connected. So it actually may not be possible to connect through from one polyhedron to another just by moving a face. But certainly, you know, then this is, you know, another case where if open source efforts combined with sort of mathematical insights could certainly have very real benefits to meshing and computer graphics in the future. So there are some very special triangulations that are used much more commonly than others. This table basically outlines two triangulations of substantial interest. I'll start with the bottom one, actually. So this minimum weight triangulation, which unfortunately is an NP-hard, you know, effectively algorithmically intractable problem, but which would be very useful for economical networking because it would tell you the triangulation for which the sum of the Euclidean distances across all of the edges in the triangulation is minimum. So if you needed to form connections between all of the neighbors in a point set, and you wanted to do that in a fashion that connects them all as triangles, and it was really expensive network, you know, very expensive network cabling that you're using, for example, you'd ideally want to have the solution to the minimum weight triangulation, which unfortunately is very difficult to get. It turns out that there are some tricks using modern computer architectures, GPUs, and so on, to get at least close to the minimum weight triangulation. But being absolutely certain that you've reached the minimum weight triangulation in an efficient fashion is certainly not a trivial process. But arguably the most famous type of triangulation of a point set is called the Delaunay Triangulation, which is named after Boris Delaunay, the Russian mathematician. It turns out the Delaunay triangulations are really closely connected to the mathematical duals of Voronoi diagrams, which is also really well known in computational geometry. And it also turns out that Boris Delaunay was Voronoi's graduate student. He was his PhD student a really long time ago. And one of the most popular applications of Delaunay triangulations is modeling terrain. So 3D maps of Earth are actually connected from a really limited data set. And we effectively have to, produce those, those sort of these terrain maps where you have sort of dark colors and an elevated three-dimensional surface for mountain ranges, and sort of lighter colors and indentations for valleys. So you have a sort of a tactile map, a topological map of the Earth's surface. It's generated from a limited number of data points that have to be extrapolated using a triangulation type approach for the regions that are in between the actual measurements taken in the real world. So we effectively define the Delaunay triangulation as, and crudely, as the fattest possible triangulation. So it's a crude, but it's actually an accurate description. It only has legal edges, which means that the edges that are used in the triangulation select the triangles with the largest possible angles. So if we look at the triangles in this example figure down here, the only difference is that this edge here on the left has been flipped to produce skinnier triangles on the right. By skinnier, I mean that they have smaller angles at the ends here compared to at the ends here, here, and here. So the Delaunay algorithms will always strive to convert this type of triangle into this type of triangle, which has the fatter angles. General position for Delaunay in the plane, so in 2 dimensions, is that no 4 points are co-circular. So if you were writing your custom algorithm, you would definitely want to check your input data for that, because you could otherwise end up with problems. So this is from the textbook I mentioned before, Devidas and O'Rourke, and they were trying to basically trying to identify or try to demonstrate the massive impact that you can have as a result of triangulating in one fashion versus another on the resulting terrain. So we have a valley using the Delaunay approach and a mountain using the non-Delaunay approach. So it is actually possible, using the sort of flip graph brute force approach to just edge flip. So you can start off with any arbitrary triangulation you want, so any maximal non-crossing set of edges, and then just flip edges. So progressively convert edges that are illegal to edges that are legal, meaning that there are fatter, larger angles, and those result in triangles. Do that over and over until you can't flip any more edges to make fatter triangles. That is actually a valid way to calculate the Delaunay triangulation, but it's slow, so it's quadratic time and complexity, and you can't use this incremental process for this edge flipping approach for 3-dimensional cases. So before we move on to some practical applications below, I just want to mention the famous empty circle property of Delaunay triangulations. This is used extensively. It's used in the duality between the Delaunay triangulation and the Voronoi diagram. And it's also it's an alternative definition, so if you find this concept of fat triangles a little bit confusing, you could also fall back on this definition, which is just as valuable, if not more valuable, than the first definition I've presented. And it basically goes as follows. So none of the original data points, which in the plot here are basically shown in green, fall within the circumcircles of any of the triangles of the Delaunay triangulation. So we can see all the triangles here. They have circumcircles, right? So circles that pass through the 3 points. And if you look closely here, you won't be able to find any data points that fall anywhere other than on the border of the triangle, and border of the circumcircles. So none of them fall within, for example, the center of the circumcircles. And actually it turns out that the centers of these circumcircles, so the circumcenters, when they're connected to neighboring circumcenters, that actually gives you the vertices and the edges of the Voronoi diagram. So that's where the duality comes from. So that's a really useful property if you're working in a programming language where, it's not the case in Python, but certainly if you're working in a language where you didn't have access to the Voronoi algorithm, but you had access to the Delaunay algorithm, you could easily get really close, at least in planar cases, to the Voronoi result by calculating the Delaunay triangulation and then connecting the resultant circumcenters of the circumcircles. But let's move on to some practical applications of SciPy.Spatial.Delaunay. And I actually struggled to find a really sort of compelling, useful example where I could convince you that this is really something that demonstrates the power of Delaunay in a practical sense. But after a bit of research, I found something I didn't actually know, and actually a really useful application of the Delaunay triangulation in a sort of larger multi-step process, which is basically the problem of connecting a set of nodes using a minimal amount of, say computer nodes by a minimal amount of wiring, because the wiring is prohibitively expensive, for example. So this sounds a bit like the minimum weight triangulation, but it's not quite the same thing. So all we need is one edge that connects all of the individual points, such that you can reach any given point in the network somehow by traveling through the network. So there don't have to be triangles in the system, and there won't be triangles in the system. We'll just have a network that connects all of the nodes, and it does so in a manner that reduces this basically has the minimum sum total Euclidean distance across the line that connects all of the nodes. So this is called the Euclidean minimum spanning tree. If we want to do this for, say a random set of 25 points, these can be 25 computer desks, computer positions in an office. The first thing we do to find this minimum spanning tree across all the nodes is to calculate the Delaunay triangulation. There are other approaches, but this one is definitely the fastest. So the other approaches will typically have a slower time complexity. So the Delaunay triangulation is actually a way to minimize the sort of the number of permutations, the number of possible routes through these nodes in the network. Now, SciPy has something really useful called the minimum spanning tree function. So SciPy.sparse. I think it's primarily placed in the sparse namespace of SciPy because many of the nodes won't be connected to each other, right? So not every computer needs to be physically attached to another. So this is basically an example of where unconnected nodes are labeled in the data matrix as 0, and so you'll have a lot of zeros in your data matrix, and so it makes sense to treat this in a data structure which falls under the sparse category within SciPy. So as my comment here indicates, it will be an n by n symmetric matrix, and you'll basically have values of 0 for self in that matrix. So the diagonal in this matrix will be 0, right? So all values in the diagonal are 0, because no node, no computer should be connected to itself with wiring. And also, if any points are not connected, so if you have two computers that are really far apart, they don't need to be directly connected, because in this problem statement, we don't need the computers to be directly connected to each other as long as one can reach another by traveling through other computers. That non-connection between computers is also represented as 0. So lots of zeros are likely to be present in this sparse data structure. So to do this, we need to know which computers are, to start off, we need this on-directed graph, which has all of these distances, and this distance information will tell us which computers are connected and which ones are not. And the initial triangulation data will have more connections that are needed, right? Because the triangle will connect a given node to at least 2 others by default. So we're going to go through that, and that's sort of how we narrow down the initial search space for this minimum spanning tree algorithm, because the Delaunay triangulation gives us a starting configuration with more edges than we need, but certainly a starting configuration that narrows down the number of possibilities. So we basically go through all of the triangle indices. We pull out their coordinates, so just taking the input points and indexing those. For the triangles, this would be a 3x3 array, so 3 vertices with their, 3x2 array, so 3 vertices with their x and y coordinates. And then we basically calculate the distances between the vertices of the triangle, so basically we're calculating the lengths of the edges, and that gives you the distance on the physical network between the computers. And then we basically populate this pre-allocated matrix here, so it has 25 rows because it's 25 computers, and it's each column is the distance between computer I and computer J, right? So with itself on the diagonal it's 0, and then you go from, for example, the first computer to the second, third, fourth, fifth, sixth, and so on by iterating through the triangle indices. So we assign all those values in the undirected graph. And just for sanity purposes, I've already executed this code. You can see that the diagonal of the undirected graph does indeed contain all zeros, so no computer is directly connected itself. So that doesn't guarantee that the code is correct up to this point, but it's certainly a good sign. And then we calculate the sparse result. So we're going to get rid of even more, because Delaunay triangulation again gives you more edges than you need because it's not the final result. We're going to have even more zeros, so we're going to have the sparse result from calculating the minimum spanning tree, which eliminates the edges that we don't need and selects only the edges that are part of the Euclidean minimum sum total spanning tree. And so basically the idea is that this minimum spanning tree is a subgraph of the Delaunay triangulation. So the answer is in there. We just need to use this code in SciPy, the minimum spanning tree code, to identify the region that's shown in green. That minimizes the amount of wiring needed to connect all the points, all the computers in the original data set. So the Delaunay triangulation here provided a number of possible solutions, and then the minimum spanning tree algorithm was used to select from that restricted subset and give us an answer much more quickly than a more exhaustive approach would require. And so I'm just calculating the total distance, which is shown in the plot here, by iterating through the sparse result. The sparse result is converted to an actual denser result, so it's a coordinate matrix, so that I can actually add in the total distance, which is measured in these cx.data values from the nodes. So if we wanted to let's just take a quick, I'll execute this once more just to be safe, and then we can take a quick look at the cx, so this data structure that we got, just to see what's going on in there. So cx, sparse matrix, yeah, so it's just telling us that. Let's take a look, I should move up a little bit farther, maybe take a look at the sparse result, see what we get from that. So sparse result, sparse matrix. Actually, let's go back to the undirected graph just to see what's going on there. So the undirected graph. So here you can see all the zeros for nodes that aren't connected, and then we see the values for nodes that are connected. But it certainly makes sense here. You can see there's a lot of zeros, so it makes sense that we're using a sparse data structure. But as you can see from my efforts, the actual displaying of the sparse data is a little bit tricky, so there's a bit of a cost to the performance gains that you get for working with the sparse data, and that's that working with those data structures requires a little bit more fleshing out. But certainly I hope this is a sort of compelling example of of how you can use Delaunay triangulations on potentially real-world problems where you're trying to do something economically in a network using the minimum amount of wiring, for example. So from the standpoint of the Python community, it's maybe useful to wonder if we have the fastest possible performance for scipy.spatial Delaunay, which we've just used. So I've set up, this is a similar benchmark code to what I was using before on the convex hull, so going up to 1,000,000 points. And you can sort of tell it's taking longer, so going up to a few seconds. So it's a bit more of an involved calculation in the convex hull. Takes a bit longer. Still waiting. So again, scipy.spatial Delaunay. This is just for the two-dimensional case. And we're going to optimize the results using either linear, log linear, or quadratic time complexity fits. These are basically chosen because I have a rough idea of how it should perform. If we rerun this, we can see that basically it looks like it's either linear or log linear. And again, we know from the literature that it's not going to be faster than log linear, and indeed it does appear to be operating with log linear performance, which is the optimum. So there's not a whole lot of opportunity, from an open source standpoint, to improve what Python, and this is really what QHall, because again, scipy.spatial Delaunay is basically just exposing QHall underneath the hood, is doing. I mean, there might be opportunities for improvement in terms of making the code run faster outside of the algorithm itself, but the algorithm proper is an optimal algorithm which is performing at a log linear level.